Hi everyone, welcome to today's topic. So this is my topic number 18, and for topic number 18 I have chosen John Taylor distortion, in short JT distortion. So this is an important topic from coordination chemistry, and which is obviously a important chapter for CSIR-NET, and this is from inorganic chemistry. So this in this video you will be learning the John Taylor distortion, the theory behind it, how it is happening. So this will be actually important because sometimes students get confused about the types of. I will be teaching you shortly. So sometimes some confusion actually arises. So for that reason, to have the theory portion, the idea of the theory portion, or how actually it actually occurs and why it is occurring. So that kind of ideas are necessary. So that I will be telling you. And after that, we will strictly go to some examples and some questions which are previous year questions. So that we will solve. And I hope you will enjoy this session and you will learn so much in this session. Okay. So let's start with today's topic. So John Taylor distortion. Distortion means some changes from ideal structure or ideal geometry. Okay. So distortion means change from ideal geometry. Fine. Distorted. When we say that this is distorted means it was like that, but it is now distorted little bit. Okay. So distortion we know. Okay. So here for coordination complexes, some geometrical distortion takes place. Now question how or when this kind of distortion we can see. So in order, so before when we have to have the idea that why distortion actually in every cases, each cases. So why distortion? Why any system goes for any distorted structure? So it is to maintain the order or to reduce the energy and the symmetry. Reduce the energy means we know that the energy profile diagram, the compounds or the states which are lower in energy that are stabilized. So the main purpose of the system is to go for a high stable or more stable structure. That is fine, right? So one important thing I want to tell you here that JT effect, this John Taylor distortion effect, is in this order. The octahedral has the highest order, then tetrahedral, then the square plan. Okay. So we will be generally here in this topic. For this topic, we will take the octahedral complex, and that will be helpful for understanding this topic. Okay. Now, the symmetrical and unsymmetrically filled d orbit. Why I took this topic? Because the JT distortion, when uh, we know why, this is the question for why, right? Why this is happening? Because of the stability. Fine. Now, when it will happen? When happens? That answer we can find out if we know that symmetrical and unsymmetrical filled orbital means what. Okay. So, symmetrically filled orbital, d orbitals it is, d orbitals, it can be symmetrically filled, can be unsymmetrically filled. So, symmetrically filled means that they are fully filled or half filled. Okay. And unsymmetrically filled means partially filled, the opposite of that. But how we can explain that? Okay, explain how we can explain. So we know that when ligand field is there, the d orbital 1, 2, 3, 4, 5, it is distorted into these two energy levels. Okay. Uh, okay. So this is sorry. This is actually wrong. So the two orbitals will have high energy and three orbitals will have low energy. This is called T2G and this is called EG, right? So fully filled or half filled. In that case, what is happened? Let's say half filled means half filled. When we say half filled, let's say in d orbital, 5 orbitals lobes are there. So every in each these orbits, 2 electrons actually can sit, right? So 1, 2, 3, 4, 5. 5 are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This D10 configuration we call fully filled. Or when we say for the D case, when you say half filled, D5. Okay, that time D5 high spin. That time every orbit should have 1 electron each. Okay, so this is symmetrical, right? 1, 2, 3, 4, 5. Every orbit has every d orbitals has the 1 electron and here 2 electron, so we can't differentiate between them. Then we will call it symmetrically filled. So when we consider T2G and EG kind of this separation, that time also 1, 2, 3, 4, 5, this is half filled, and when we the full filled case is this. Okay, so in the case of fully filled or half filled, or this is D10 and D5 I said, and for this kind of separation D3, because then T2G 3 and EG 0. So we can't differentiate between T2G orbitals and we can't differentiate between EG orbitals. This is D3. This is also symmetrically filled. Okay. So every orbital has same electron density among the T2G and fine. So D3, D5, okay, D6. No. Again, it can happen when, let's say when D5 is there. Okay, D5 we know that it is symmetrically filled, and then 1, 2, 3. So it is D8. So for the case of D8 also you see that T2G, every T2G orbital has 2 electrons and every EG orbital has 1 electron. So in this case this is D8. D8 case also it is symmetrically filled. So what we got actually? How much? How many we got? We got T3 when T2G are symmetrically filled and EG also, D5, D10 and D8. These 4 cases, when these 4 cases are asked for, in the case of these 4, the symmetrical field orbitals are there. Fine. What will happen? In these cases, there will be no distortion. Whenever in a question that is asked that among of the options which doesn't show any distortion or John Teller distortion, the answer will be among these 4. Okay. So now partially filled, unsymmetrically filled means it can be any other than this one, right? So D1 can be there, D2, D3 no D3, D4, D5 will be not there, D6, D7, D8 also will be not there, D9. Okay. So 1, 2, 3, 4, 5, 6. Okay, 6. Among them, high spin, low spin are also there. So another case I want to tell you that whenever that low spin D6 complex is there. Okay, so I'll draw it here. Low spin D6. Very important. Low spin D6 means the electron will be paired first. So 1, 2 and 3, then 4, 5, 6. This is D6 low spin. In that case also it is, see, we can't differentiate between orbitals. So this will be D6 low spin, will be symmetrically filled. So whenever any options are given, don't try to remember that. Okay, D5, D10 you know, D3 also you know. But whenever any option is given, just try to separate, like fill the electrons in T2G and EG. Okay, then you can understood. Okay, so that is the thing here. So we have to consider high spin and low spin also. So fine, in these cases, in the case of high spin and the low spin, both will be the unsymmetrically filled. Okay, okay. Only D6 has when it is low spin, it will be symmetrically filled. Fine, you can do that, right? So in the case of unsymmetrically filled, what is there? The distortion will be there. Fine. The JT distortion now, we know now that whenever partially filled orbitals are there, means the unsymmetrical filling of the orbitals are there, that time JT distortion can be seen. Fine. There will be again two kind of JT distortion. By that filling also, unsymmetrical filling. The strong JTD and the weak JTD. So how can we say which one is strong and weak? So in that case, it is told that whenever the EG orbital is unsymmetrically filled, okay, and for the case of weak JTD, T2G orbital unsymmetrically filled. Okay, so it is say, let's say for example, D9 system I am taking 1, 2, 3, 4, 5, 6, 7, 8 and 9. So here in T2G it is symmetrical, but this EG is unsymmetrically filled. This is D9 system, right? So in that case there will be strong JT2. Okay, please try, please remember this, not try to, please remember this. Okay, so it is said that it is actually in high energy. So the interaction with the ligand, okay, if it is unsymmetrical, will be more. Okay, so there will be strong JTD. And for the case of weak JTD, what will be there? So let's say we are taking D2. Okay, so let's say D2 is there. D2 or then what will happen? D1, 2. So unsymmetrical filling of T2G orbital, that time it is weak JTD. Okay, so whenever various options are given, okay, and you are asked to say about what is strong and what is weak JTD, that time now you can tell, right? Now we can tell the answer. Okay, fine. Now the types of JAHN Teller distortion. This is the main important thing which we have to understand clearly. Fine. I am teaching you in a step by step manner. Okay, just try to listen carefully, you will understand it. Okay, so types of JAHN Teller distortion is two kind of, Z out and Z in. I hope you know these terms. Okay, so now what is Z out? Okay, let's see. Z out, when axial out means when axial bonds in a octahedral complex are elongated than equatorial bond. Elongated means more, the bond length will be more in Z direction. So let's say this is actually, for the case of complex, we take this is Z, this is, let's say, Y, this is X. Okay, so the axial bonds which are in the direction Z axis direction, that will be elongated than equatorial. In that case, this kind of distortion will be called Z out distortion. When it will happen? So before going to the when question, first look at the d orbital, how the lobes actually are arranged in 3 dimensions. So this is dyz, this is xz, this is xy, x square minus y square, and dz square. Fine. So what are the important things here which we have to note down? One is The lobes of dx square minus y square and dz square lie in the axis. Along the axis, it will be along the axis. Means, see, this is y and this is x, na? So in dx square minus y square, the lobes are in x and y axis. They lies in x and y axis. Okay, and also in dz square. This is through dz square. The orbitals are actually arranged. But in the other cases, see, they are not lie along the axis. They are in between axis. See, this is between yz, right? Here this is between xz, like that. So these 2 points we have to remember. Okay, first this dx square minus y square and dz square lie in the axis, which are actually consist which dx square and y square, dx square minus y square and dz square are called EG, which I was talking about, that T2G and EG. So T2G are this. Okay, the same thing actually written, but here the T2G will be dxy, dyz and dzx. These three are called T2G, and here lobes are in between axes. Fine, these 2 points you have to remember. Now the Z out, how it happens actually. Let's say we have taken one complex, this is ML6, this complex, okay. All bond lengths are same, fine. But when it will convert it to this, for example, if we take, imagine we took one metal which has more electron density in z-axis. So more electron density in z-axis than other. Z-axis has more electron density. So how it affects? So when ligands are approached, so we know ligands has the electrons, lone pairs or electrons which they donate to metal, right? So z-axis has, when more electron density, the ligands are actually the ligands face more repulsion to z-axis as it has high electron density. Okay, so for to gain the stability, because whenever they come closer, the repulsion will be more. So to gain to have the stability, they the bond length, they actually form bond with far away from the metal. They form bond a little far away from the UGI. Okay, so that's why the bond length is more here. See, so you know now. So whenever z-axis has, in the z-axis, z direction, because the lobes actually decides that whenever the z square, or whenever the x and y has the more electron density, that will depend on the energy versus the lobes arrangement, how they are actually arranged in energy profile diagram, and how the electrons actually fit. That we will come in the next slide, but in this slide try to understand that whenever ligands are coming with electrons, they face more repulsion through that z-axis. Okay, as it has more electron density, that's why they keep some distance than usual from the metal, okay, and from the bond. So that's why it is called Z out. Fine. So when z-axis has more electron density, the repulsion with ligand will be more along z-axis. The bonds along z-axis will be more to reduce the repulsion, to get stability. Okay. Now coming to the previous thing, which we actually we were reading, that T2G and EG orbital, the splitting happens. Now for the case of Z out, what will be the splitting? So for the case of Z out, you have to remember that the dz square orbital will be less in energy than EG. Okay, let's say this space is delta 1. So dz square has little bit of less energy than Eg, and his x square minus y square will have the highest energy among all. So energy order will be, and like the same way as dz square has less energy, like the same way dxz and dyz, the orbitals which has z, okay, that will have less energy. Okay, that will be more stabilized. So the order of energy will be dxz equal to dyz greater than dxy. These three are T2G, we know. T2G actually split it, and then dz square, then dx square minus 1. Sometimes in the question, these kind of energy order also can be asked, that in the case of Z elongated Z case or Z out case, uh, this that kind of distortion, what will be the energy order of the d orbitals? Okay, fine, you know that. So now just try to remember that along the Z axis ligands are coming, that's why ligands faced. And one more thing was there, along the Z orbital, Z axis, more electron density will be there. So let's say for the Z out, the one of the example is the D9. Okay, let's just fill out and see what will happen. Okay, so for the case of D9, what will happen? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so see which axis, through which axis electron density is more. So through, let's say, Z axis, we are now saying considering Z axis, right? So 1, 2, 3, 4, 4, and 5, 6 electrons, and the other 3. Let's say this will be also there because x and y is also there. So 1 and 2, 3, 4. Let's say 4 is there, but here only 1. In the EG also, seeing the EG, you can understand that this is x square minus y square, and it has 1, but it has 2. So z square or along z axis there is more electron density, right? So in this case, there will be more repulsion through z axis and bond will be elongated. Fine. So through z axis bond will be elongated, but whenever energy wise we will write or draw the d orbitals, then dz square will have less energy than dx square minus y square. Okay. Sometimes students get confused, and they actually depending on the name, z out is written, right? So they just take that inverse. Okay, so they think that the z square will have the more energy, but this is wrong. You have to understand why, because of the electron density which I told you. Okay, now coming to the again types, Zn is left. So in the case of Zn, when the equatorial bonds, Zn means through the z direction bond is lesser than the other. Okay, so through z orbital, this will look like this. Okay, this. So seeing the picture, you must be thinking that through z actually the bond becomes shorter, but that is not the case. It will happen when equatorial bonds, this is z, this is y, and this is x, right? So through x and y actually the elongation happens, this kind of elongation. Okay, that these two bonds actually will increase, these four bonds will increase, so that it seems like z is through z the bond length decreases, but that is not the case. Okay, so this is z, it looks like this, that through z bond length is small. Okay, so yes, so when it will happen again when x1 y has more electron density than z axis. Okay, the opposite thing actually, The repulsion with the ligand electrons will be more along x and y axis. So the bonds along x and y axis will be elongated to reduce the repulsion. Same, just in the place of z, here it is x and y. Fine. So in the case of Zin, again the same thing, but not same. Why? See here. Here the change you can see. So the Z through the Z will have now less electron density. Okay. So it will have the high energy. And like the same way here also Z is in high energy than Eg, and then Xz and Yz will also have the high energy than the T2G, okay, than the previous condition, right? So this is just the opposite of Z out. If you can remember the conditions or how this arrangement of orbitals energy wise is for Z out, you can easily draw it for Z in also. Okay. So let's say in Z in case, so what can be there? D1. Okay. D1 it shows actually Z. So in this case, see, X and Y has more electron density than Z. Z has no electron density. So through X and Y, when ligands are coming from X and Y, they will face more repulsion. That's why from the far away, they actually form bond with metal. Okay. So now you understood Z out and Z in. So now distortion for different D configuration that we will see. Okay. So Z out and Z in. Okay. So for different case, let's say T2G and EG. Okay. Let's say D1. D1. It will show distortion, right? Let's say D2. It will also show distortion because unsymmetrical filling. D3, it will not show, right? So D1 can show, D2, okay, in general I am saying distortion, okay? D1, D1, D2, okay? D3 can't, now D4 can, D5 not because symmetrical filling will be there, then D6, high spin. This is high spin, and D7, okay, this is D7 high spin, okay, and D8, it will not show distortion. D9, it will show distortion, but D10 again will not show distortion. This is the filling is high spin filling, which I show you. In the case of low spin, 1, 2, 3, and after that 4, which will be distortion will be there. D4 low spin, D5 low spin, D5 high spin will show will have the symmetrical arrangement, so it will not show distortion, but D5 low spin has distortion. Okay, D6 will not, D7 will have distortion, D8 will not having any distortion, D9 distortion will be there, and D10 no distortion will be there. Okay, so by seeing the arrangement I have told you, but I will take some examples. Right now in this slide actually I want to tell you that in which case actually Z out and in which case Z in kind of distortion can be seen. This you have to remember actually. So the Z out will be shown by T2G1, okay, and T2G4 means D4 low spin. So T2G1 means this and T2G4 means D4 low spin. 1, 2, 3, 4. This one. Okay. These two will show ZD, and uh, actually special example is there, that is CUF3, that will also show ZD. Okay. These three you have to remember. and rest of the others actually the Z out. Okay, the rest other everything. Let's say T2G2, T2G4, 6, low spin, sorry, high spin, everything it will be Z up. And in the whenever strong distortion is there, that means EG orbital is unsymmetrical. Well, that time strong distortion and weak is T2G unsymmetrically filled. Okay, these things you have to remember. Which one is showing the ZE? So T2G1 and T2G4. Okay, and CUFT you can remember. And rest things are showing Z out. And which case the distortion is more or strong? Whenever EG orbital is unsymmetrically filled, like Cu copper 9, and whenever T2G orbital is unsymmetrically filled, that time lower ZT distortion can be seen. Okay, let's take some examples and understand this. Okay, scandium, we know 3D series, right? We should know. So scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, and nickel, copper, zinc. So D1, D2, D3, D4, D5, D6, D7, D8, and D9, D10. And 4s2 is present. This is 3D series. Okay. So for the case of scandium, this is D1 and scandium 2 plus means D1, 4 is 0, right? So in the D orbital, there will be, okay, we know the splitting T2G and EG, so D1. So in that case, it will be Z in distortion. Okay, so the structure will look like Z in means through Z actually bond length is less, it seems like, because these are more. Okay, OH2, OH2, and OH2. Fine. And chromium 3 plus, okay, chromium is, we know D4, but chromium 3 plus will be D3, and we know for the case of D3 what will happen, symmetrically filled, it will be no distortion, it will show distortion, it will have no distortion. Okay, now chromium 2 plus, means D4 we know, and D4 it is high spin because this is weak field ligand, H2 is. Whenever strong field ligand like cyanide, CO, nitrosyl that are present, that time low spin complex will be there. Okay. So 1, 2, 3. So D4, 1, 2, 3, high spin, 4. Unsymmetrical filling, tell me it will be strong JAHN Teller distortion or weak? What we have to say? See, it is unsymmetrically filled in EG orbital, right? So strong distortion. Okay. So strong distortion will be there for the case of D4 high speed. Fine. Now FeCN whole 6 2 plus. Fe we know D6, right? And Fe 2 plus means D6 4 is 2, 4 is 0, right? This is 4 is 2. Now one important thing is that D6 can be high spin and low spin, but here a high field ligand, the strong field ligand cyanide present. So it will be low spin complex. Means pairing will happen. T2G and EG, let's say, it will be filled like 1, 2, 3. Then again pairing will happen 4, 5, 6. It will be symmetrical. So no distortion. Fine. The copper 9, D9. It's high spin and low spin both has the same arrangement. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it is unsymmetrically filling and in EG orbital. EG orbital is unsymmetrically filled. That means JTD will be there, and strong JTD. Okay, strong ZTD will be there. Next, the CONH3 whole 6 2 plus. Okay. It is D7 configuration, D7 CO2 plus, and it will be 1, 2, 3, 4, 5. So NH3 is not so much high field, so that's why it will not pair up. 1, 2, 3, 4, 5, 6, 7. Tell me, it is strong or weak JTB? So here Eg orbital has 1 and 1 electron, so it is symmetrical. But here T2G orbital is unsymmetrically filled, so it is weak JTB. And obviously it is Z out. This is also Z out. Okay. Now coming to the question, it is asked in GATE 2000. So the compound which exhibits JAHN Teller distortion is. So we have to first have an idea about the electronic configuration of the metals. Okay. Mn2 plus, the A option, Mn2 plus is D5, right? B, Mn3 plus, it will have D4 configuration. Fine. C, chromium 3 plus, D3, D, Fe, it will be 2 plus because cyanide has negative charge. So Fe 2 plus, okay, here actually this was wrong. It will be 4 minus. Okay. So Fe2 plus means D6. Now tell me which exhibit JAHN Teller distortion. D5 we know symmetrical filling will be there, it will not show. D4 if it is high spin, 1, 2, 3, 4 unsymmetrical, and in the case of low spin also it will be unsymmetrical, but it will be Z in, right? Okay. Here only distortion we need, so it will show distortion. Just check other options. This is D3 symmetrical, no. This is D6 and strong field again. It will be pair up, so D6 low spin doesn't show. Fine. So B will be the answer. Next, the correct statement of MNO bond lengths in MnH2O whole 6 2 plus is. This is CSIR-NET question. Okay. So see how simple this question is, but you have to have the idea about JT distortion when the compound will give the JT distortion. Okay, if the distortion is given by the compound, if it is Z out, then to Z axis bond will be elongated. So all bond lengths will be not same, right? And in the case of Z in also, but in that case, to Z actually bond length will be less than the other. Okay, so Mn2 plus, again D5, right? So D5 case symmetrical filling doesn't show any distortion, no distortion. So all bond lengths will be same, all bond lengths are equal. This will be the correct option. Okay. Now identify the correct statement about these two complexes. Okay. Again, in the option C, the bond lengths are there, equatorial, axial, like this. Okay, first we have to have the idea that Ni2 plus means it is D8 and copper 2 plus means it is D9. Both has H2O, weak field ligand. Okay. But for the case of D8 and D9, weak field and strong field both has the same configuration, electronic configuration. So 1, 2, 3, 4, 5, 6, 7, 8. And here 1, 2, 3, 4, 5, 6, 7, 8, 9. Unsymmetrical filling of Eg. Strong ZTD and Z out. And strong. And in this case, no distortion. Right? So no distortion means all NiO bond will be same. But in this case, two axial bonds. This is Z out. The structure will be like this way. copper, let's say this will be H2O, this will be the H2O, and the rest bonds will be this and less. Okay, get out like this. So which option will be correct? All NiO bonds, no, no, equal, that will be not the case. NiO equatorial and CuO equatorial. What? This should be not. All NiO bond lengths are equal. This is correct. Whereas CuO equatorial bonds are shorter than CuO axial bond. This is correct, right? This equatorial means equatorial bonds are where? This one, these are equatorial, and these are axial. So axial bonds lengths are more than equatorial. So C will be the answer. So equatorial bond lengths are shorter. This will be the answer. This is also CSIR-NET June 2014 question. CSIR. Okay. See, these kind of questions are there, and also in some cases that straightforward questions are also asked. So I hope you have understood all the things when a complex shows Z out, when Z in, right? When distortion will happen, when not, like symmetrical and unsymmetrical, and the weak distortion will be when T2G is unsymmetrically filled, and when strong distortion will be there, that time EG will be unsymmetrically filled. Okay, so point wise. So in this slide, I will show you one will be the symmetrical and unsymmetrical filling. These you have to understand that when we call it symmetrical and when unsymmetrical. Okay. Second one is when Z in, when Z out. When, and third is the and third one is the okay, when strong and weak. Okay, these three you have to understand properly in this topic. So I hope you have understood all this topic, all these things, these points. I have tried to teach you, or I have tried to deliver you a speech like easy manner so that you can understand it properly. So I hope you have enjoyed it, and see you in the next session. Okay, thank you.